3 for Physics 2211 by Justin Chu. So in the introduction, in lab 3 I observed a spaceship and planet orbiting around a black hole, and was asked in part 1 to find the mass of the black hole using the planet's motion with the net force. And in part 2, I was asked to find the ship's velocity as it curved around the black hole, where I would use Newton's second law and all forces acting upon the planet and the ship. And the mass of the black hole was found to be this number, found in GlowScript, and the magnitude of the ship's velocity was found to be this number, also found in GlowScript. So the system and surroundings. So the star is the system, and the black hole is the surrounding acting upon the star in part 1. And in part 2, the ship is the system, and the black hole and the planet are acting upon the ship. So Newton's second law was used a lot in this lab, and basically it states that an object in motion will stay in motion unless it's influenced by an external force. And from the second law, we get F equals ma, and we also get delta P, or the change in momentum, equals F times the change in time. And other related equations that we used from Newton's second law are the position and velocity update formulas. So this is a circular motion problem, so we also have parallel and perpendicular forces in both parts of the lab. So the p hat and n hat vectors refer to the parallel and perpendicular forces. And then using Newton's second law, we can also derive that the force equals the change in momentum over the change in time. And from there, we can conclude that the force in the p hat direction will be the delta p over delta t that we found here for the force. And then the force in the n hat direction for the centripetal will be mv squared over r. So it's also universal gravitation that we use to find a lot of the forces in this lab, as it is a system of two objects and a black hole. So the equation looks like this, and is negative g times m1 times m2 over r squared. And this is negative because of the law of attraction of two objects. So it's an attractive force. And then g is the gravitational constant, and m1 and m2 are the masses of this object in the system, and r is the magnitude of the distance between the two objects. So in part 1 of GlowScript, these are my initial conditions, with delta t representing the amount of time in a day in seconds. And so basically what happened was, so we used the initial v initial and v final, our two velocities, to find the delta v, and then we used and the p equals mv, the momentum. So we found both delta p and delta v, and from there we can calculate with delta p, we can calculate the dp dt, which equals the force. The F net equals dp dt. And then from there, using the force net, we can calculate the perpendicular and parallel forces, which can then give us the mass of the black hole. And these are the things I got from my GlowScript. These are the numbers I got from my GlowScript. And then using the mass here in part 2, we are solving for the ship's velocity. And so first we have to start with finding each of the forces using the gravitational force equation. And then from there, we can plug the force into the velocity and position, velocity update formula. And then from there, we can find the new velocity and find the new position for each one of the planet velocity and the ship velocity. And then from there, we can find the ship's speed to be equal in magnitude to this number, which I found by plugging these constants in. And this is what it looks like in the graph of the GlowScript with the motion curving around the black hole. And so possible sources of error for this lab include inconsistent entering of values in scientific notations. So what does this mean? So basically, in this question, it's asking us how the net force is different from the change of momentum, and it's not. The net force is the rate of the change of momentum, and therefore we can use the rate of change of momentum to calculate the forces in this lab. So it's not different, the rate of change in the net force. And for the what if, it asked us to find the ship's velocity as it enters the black hole. And so in order to enter the orbit of the black hole, my velocity must be slightly high. My velocity must be similar to the planet, but also be slightly higher in starting y position and slightly lower in x position. But this would be the speed. I would just need to start from a higher position and a slightly lower x position. Thank you.